Yannis, I guess you can start.
Yeah, sorry, I was muted.
Okay, so 1, 2, 3, go.
Okay, hi, my name is Yannis Wolf. I'm a research engineer at the Barcelona Supercomputing Center, and together with Mandar Harshe from the company Klepsydra, we're going to present our joint work on onboard cloud detection using neural networks for Earth observation and in-orbit demonstrator case study. Clouds are playing a pivotal role in shaping the climate. That's why the Earth Observatory Lab of NASA has been observing them for decades now and creating these kind of cloud coverage map that you can see here in the center of the slide. They show what's the average cloud coverage in all areas around the globe by month. And it showed that about 67% of Earth's surface is typically covered by clouds. Together, the data for these kind of plots, we need quite modern optical instruments like moderate resolution imaging spectroradiometers in this case, that are situated usually in quite huge satellites, like in this case NASA's Terra satellite, which is a huge satellite weighing more than 5 tons. But recently, for Earth observation, some new kind of satellites emerged, small nano satellites, like for example ESA's OPSAT satellite. They feature only very simple optical measurements. But as an advantage, they only weigh like 7 kilograms. Now, the challenge that they pose is to measure cloud coverage with these small nanosatellites with only simple optical tools. This could pay out very well because cloud detection can enable new technologies like cloud detection as a crucial pre-processing task. It can be used before another onboard AI task, for example, ship detections. This is an object detection task, which usually precise object detection models are very computational heavy. So we can only run ship detection on cloud-free images, for example. So we save some precious computing resources. And another example would be to reduce downlink size. The downlink speed on small satellites is very slow. So not sending cloudy images that don't contain any information or graying out areas that are full of clouds can reduce this file size that we're gonna send down to Earth. This presentation is split into 2 parts. The first part is going to be presented by me. It's about the design, training, and testing of a cloud detection network. I'm going to define the cloud detection task in our study. I'm going to show the data set that we used, the neural network structure, the quantization that we used before deploying. And I'm going to show some results visually and also some accuracies that we calculated. Then, in the second part, Mandar is going to take over, and he's going to talk about the runtime performance evaluation. He's going to show how Klepsydra AI optimizes the inference of the, neural networks. He's going to show the deployment on an OPSAT demonstrator board that we did. And in the end, he's going to show some results on the runtime of these. So let's dive right into the design, training, and testing. Cloud detection is nothing inherently new, but it's sometimes a bit of a fuzzy term because in some works, it's only if there are clouds present on an image or not. But in our study, we define cloud detection as a segmentation task. Image segmentation means each pixel gets a specific label assigned. In our case, this can be, is this pixel representing a cloud or is it not? In this figure, you can see the input image will yield after the inference to the network a binary segmentation mask that either has 0 for no clouds or a 1 for this is a pixel that shows a cloud at any pixel. The dataset that we used is a fantastic open source dataset called Cloud 95. It contains 95 Landsat 8 images with very large resolution, around 8,400 times 8,400. Like in every AI task, any AI learning task, we split the dataset into training and validation to first train our networks, and then the final network is going to be tested on 18 scenes that are actually the official test set of this dataset. So you can also compare to other work from other scientists. The dataset is images with 4 channels, red, green, blue, and near infrared channel. And then another design, a little detail on our training is that the training and inference has only been done on small patches because training on these huge resolutions is not possible memory-wise. But it's not a resize or downsize operation, but actually we took patches, we cropped out patches from the original pictures. So as a neural network structure, we based our network on the UNet, which is, it was developed for biomedical image segmentation, but in the last years, it became the de facto standard for neural network segmentation models. The name UNet stems from the network structure that resembles a U. So we have this encoder-decoder structure. And the encoder serves as a feature extractor by having a series of convolution and max pooling layers. It downsamples the feature maps while creating more. And in the decoder, we now reconstruct these feature maps to get back the spatial resolution to output the segmentation mask. The success of this UNet actually came from the idea of these skip connections, that before every downsample step, we create a skip connection to the upsampling, so the UNet retains some spatial information to reconstruct in more detail. Features of our network are that it's fully convolutional, which means that we can have variable input shapes, which is nice because if we train on small patches, in the end, in a real application, you could actually use the full image, which would process longer, but you wouldn't have to do any restitching in the post-processing step. And our network has 5 million parameters and is 20 MB memory footprint at the moment. But a technique that is used after before the deployment, after the training, but before the deployment on very resource-constrained processes is called post-training quantization, in which we convert the weights of the model from floating point values to 8-bit integers. So these have very different ranges, these data types, as it's obvious with 32 to 8 bits. But it works because usually neural network weights are very small. And we can even, while we train, put an L2 regularizer, which enforces these very small weights. So we map these float values into the range of the integer 8. This can be seen in the figure here. And like this, we obviously have a model compression from 32-bit to 8-bit data types. We can reduce the network size by 4. We will have a latency reduction because now we only have integer arithmetic, which is usually easier to calculate. But this all comes with a trade-off. So model accuracy can potentially decrease as it's not always possible to map perfectly all the float values in the whole integer range. For our cloud detection model, this means that the memory footprint from before, from 20 megabytes now, goes down to 5 megabytes. So let's show a little bit. Let's see a bit of the test results. First, I want to give a quick look on some visual results. I chose on the left here this input image, which is interesting for me because it has some clouds on it, but it also has ice and snow on it. So this is something that original and traditional methods like FMask that are decision tree based and more look into the color schemes are failing to distinguish between ice and snow. And in the center here, you can see the ground truth where all the clouds are placed. And on the right, we see the predictions of our floating point network. I highlighted false positives in blue. So if the network here, for example, cannot distinguish between snow and clouds, this is a false positive. False negatives, where the network forgot to predict some clouds. This is usually here, you can see it at the borders around clouds. And what we can see here is that actually the network performs quite well distinguishing that, apart from maybe in the bottom left. So there is some limitations to it, but we were actually surprised how well it worked. And let's put this into numbers, because this is just the visual results. We calculated the precision and the recall. So precision means pixels that are predicted as clouds are indeed clouds. And the recall value means from all pixels that are clouds, so that are on our ground truth are really clouds, how many have been predicted as clouds. So these are a little bit detrimental. They have like an inverse relation. If you have a model that has a very high recall, so it's like probably also predicts snow for clouds, the precision is going down. So there's the F1 score that combines both through a harmonic mean. And we can see that the precision drops from our floating point model to our integer model, actually by 5 points, by 5%. But actually the recall goes up in our integer models. So if you calculate the F1 score, we can see that in the end, our model only performs 1%, about 1% worse by the quantization. And this is quite a nice achievement. So to conclude part one, I showed how we trained a UNet for cloud detection on the Cloud 95 dataset. We can see that the F1 score of 88% is quite promising for such an application. The post-training quantization only slightly decreased the F1 score by around 1%. And then we showed in the visual inspection that actually, even though it's limited, we have some robustness against ice and snow. So before I hand over now to Mandar, I wanted to note that this model is developed and published as part of ESA's open source OBP-MarkML benchmarking suite, which is a set of real-life payloads for space processors to evaluate their computational capabilities. And also, this model is going to be deployed as a use case demonstrator on our RISC-V Metasat SoC in the Horizon Europe Metasat project. So if you're interested in a high-performance multicore and a new high-performance multicore SoC with an AI SIMD unit and a RISC-V GPU, you should maybe also check out our other work. And yeah, now I'm gonna hand over to Mandar. Thank you.
So now that you have a model and you want to run it on a constrained edge device, we run into different problems. One of the problems is that even though you have modern hardware, if you use old software techniques, you get limited by how much data you can process. Now, computers max out on low to medium data volumes because of inefficient use of resources. Most of the times they're waiting for data rather than processing the data. And this ends up causing excessive power usage for low data processing requirements. So this is caused because you're using log-based parallel processing. So you have multiple threads using logs to access a shared resource. And they are most of the time waiting for the logs to be released before they can access the data. When they get access to the data, there's a context switch, and this can be expensive. And all of this makes the computations non-deterministic. So the CPU usage also fluctuates, and it's very hard to know exactly how much time certain calculations are going to take and how fast it's going to go. Klepsydra AI is one way to deal with this. And one of the problems you see in standard processing, which Klepsydra avoids, is that in this image, for example, you see that there is an AI process which is waiting for images to be loaded into the processor, and the CPU usage is low in this step. And when the AI model is actually processing the image, the CPU usages go high. So with Klepsydra AI, if you use lock-free parallelization with event loops, you can avoid these problems. So what we do is that we use multiple event loops with lock-free parallelization. Each event loop is distributed to a different thread. And this allows us to control finally how the image can be processed and how we can distribute the different threads onto different cores. So let's say we have a system with 4 CPU cores and you have 4 event loops. How would you assign these event loops to different cores? There are multiple ways. You could either just put one event loop per core and be done with it, or you could take a subset of the cores and assign all the event loops to those subset of cores. And then if you do that, you have multiple different configurations. You can split the event loops equally, or you can split them over different cores unequally, or put all the event loops on a single core and use the rest of the CPU cores for other purposes. So the performance in each case will be different. The second thing that Klepsydra AI does is that use these remaining cores for the second dimension of parallelization, which is the traditional parallelization. So what you're doing is that you have a layer which has a highly CPU intensive process or a calculation to be done, and you use standard parallelization or vectorization to perform these calculations. So in this image, we are showing matrix multiplication as an example, where you can split the matrix multiplication task into various subtasks, which can be performed in parallel using vector operations and so on to get the output as fast as possible. So when you use these 2 dimensions of the threading model provided by Klepsydra, you can have many different kinds of configurations. You can either have one event loop per core and no parallelization and vectorization at all, which gives you a low CPU usage but high latency, which is shown on the left. Or you could go with the standard approach with all the event loops on one core and using the remaining cores to do the parallelization of the operations. And this gives you the high CPU usage with low latency. And somewhere in the middle is the golden mean that you want to use in your exact application. It depends on exact application that you want. So Klepsydra AI allows you to choose these different configurations. Now, in the cloud detection model, which we have in this case, we have certain restrictions, which is that we are going to have some concatenation layers because of the skip connections. And these concatenation layers, if they are on a single event loop, they offer the nice advantage of being single threaded. So you don't have to worry about locks, internal locks. Additionally, you have the convolutional layers and the convolutional transpose layers, which are very CPU intensive layers. So you want to be able to assign them to certain event loops and also allow them to have parallelization enabled. How you choose this becomes an interesting problem to tackle. And what we do is that we generate different possible configurations for the hardware that we have and do a search and measure the performance of Klepsydra AI on all these configurations and choose the best number of event loops, how the layers are allocated to these event loops, and choose the best threading model. Now, Klepsydra AI allows you to load ONNX models directly. It has support for 8-bit quantized networks, and depending on the hardware, a 32-bit floating point networks also. What it does is that based on the model architecture, it allocates layers to different event loops. Klepsydra AI supports x86 architecture, ARM, and also RISC-V processors. One quirk of quantized ONNX models is that the convolutional transpose layer, which we use in this network, has no representation in the ONNX file format. It's represented as a series of 3 layers: the dequantized to float, the convolutional transpose, and then the quantized back to float to integer format. So this is not what we don't want to do, these 3 steps. So what Klepsydra AI does, the only minor modification to the network is that it groups all these 3 layers and does the actual quantized transpose convolution, which is required for this inference. The hardware we are testing on is a Mitisom 5CSX processor with 2 Cortex A9 cores. It has 2 GB of RAM and runs at 900 megahertz. It also has a FPGA, but we don't use the FPGA accelerator in this test. We are doing all the calculations on the CPU. And based on the methodology I just described, we perform benchmarks on different configurations on the CPU. And what we find is that when you have a single event loop and 2 threads for parallelization, your average CPU usage is around 86%. And your RAM usage is quite nice. It's 182 MB, and you get a latency of around 11.7 seconds, which gives you a throughput of around 0.06 hertz. So every 16 seconds, you can send in a new image and get a prediction of the image. If instead you use 2 event loops with 2 threads, the CPU usage goes slightly higher, your RAM usage increases, but your latency improves slightly. So you get the result faster, and your throughput is still high. The range of performance is not so much different between different configurations because we only have 2 cores. But the idea remains, which is that you can select what kind of performance you want. If your latency is slightly important, you should use the second configuration rather than the first. So yeah, this is how you can choose and fine tune the performance for the use case that you have, and you can run your inference model on board and get your predictions in a reasonable amount of time. So what we have shown in this work is that AI-based cloud detection is feasible. You have good recall and good accuracy, and these calculations are robust as shown in the first part. You don't need expensive hardware. Smaller visual sensors are sufficient to get good enough results. And if you have a good inference engine, like with the capabilities like what Klepsydra provides, you have fine-tuned control over the performance, and you can do AI inference on board. And you can do this with acceptable latency. So you're not spending too much CPU to get result too late. What we are going to be working on in the near future is do an in-orbit demonstration of this on the OPSAT, so on the actual satellite in space. We're going to load this inference engine and the model on the satellite and perform a cloud detection from the satellite itself. We also plan to benchmark this approach using other RISC-V processors, and also test using the hardware accelerator. So for example, the Dataset Sparrow, use that in order to accelerate the inference on the device. So that's been our work. Thank you very much, and glad to share our work with you. Thank you.